All right, Algebra 2, 7.2, multiplying and dividing radical expressions. So starting off, we want to say, well, let's just look at root 16 times root 9. Well, we can either say that that is, let me write that correctly, 4 times 3, which is 12, or, and what's going to be new, is going to be, this is the same thing as root 16 times 9, which is root 144, which is 12. So we can get it either direction. And what we need to say here, and what a lot of this lesson is going to be about, is that if the square root of, or the nth root of a and nth root of b are real numbers, right? So if it's an even root, we can't have a negative under there. So if those are real numbers, then the nth root of a times the nth root of b is equal to the nth root of a times b, right? This is just the general form of what we wrote over there on the left side with that root 16 and that root 9. All right, so that'll be useful sometimes. So let's do some examples and show that. Number one, we're supposed to simplify on all these. Simplify. So we have root 2 times root 8. Well, we know that because those are both square roots, we can put them together. So this is going to be the same thing as root 16, which is 4. Number 2, we're going to have root negative 2 times root 8. And we want to look at that. What could we simplify that to? Well, if we were to reread what I wrote up here, it talks about they have to be real numbers. So we can't have a negative under our root. So actually, whenever we simplify there, we really aren't supposed to be able to, right? So we'd say none. There's no square root of those, right? Just to show you what we could do, right? If we were using the complex number system, we would say this would be the root negative 2 times 8. This would be root negative 16, and there's no square root of that, right? So if we were using the complex number system, we would use that. But for what we're doing, we're just going to say no. There's nothing there. And just to make sure that we know how to generalize this, in the third example, we're going to do the cubed root. So we're going to do the cubed root of 3 times the cubed root of, we'll say, negative 9. All right. Now, the negatives under the root don't, that rule that we can't have that doesn't apply here because it's a cubed root, and cubed roots can have negatives. So here we can put these together. This is really the cubed root of 3 times negative 9, which is the cubed root of negative 27, which is negative 3. Right? The cubed root of 27 is negative 3. So the important piece about that example is to know that just because, well, we normally deal with square roots, right? But this rule applies to all roots, not just square roots. All right, next little theorem, the idea that we have, we're going to say if the nth root of a and nth root of b are real numbers again, and we have to also say one more thing. If they're real numbers, and we're going to say b is not equal to 0 here, okay? That'll make sense in just a second. So here I need a little and symbol there. Then the nth root of a on top of the nth root of b is equal to the nth root of a over b, right? So the reason that we couldn't have b being 0 there is because we can't have a 0 in the denominator, right? And one more idea that we need to remember is that we have to rationalize the denominator. Right? And what that means is that we cannot, you cannot have an nth root in the denominator. You can't have that in the end in your final answer, right? You can have it in the middle of the problem, but you can't have it in your final answer. All right, so next example that we have here, example number 4. Again, we're just simplifying. We're going to say, what is the cubed root of 32 over the cubed root of negative 4? Well, neither of these we can reduce really quickly. Actually, there's not like a perfect cubed root for either of these. But what we can do is we can turn this into one big fraction. We'd have the cubed root of the fraction 32 over negative 4, which is the cubed root of negative 8, which is negative 2. Very nice. All right, example number 5. We're going to say we have the square root of 243 over the square root of 27. Again, because those are the same type of root, and I don't know if I've emphasized that very much. In example number 4 here, they were both cubed roots. Here, in number 5, they're both square roots, right? There's nothing written there, so it's a square root. They have to be the same root, the same type of root for you to combine them like this. But in this one, they are the same root, so we can combine them. So we have a big root, 243 over 27. That can simplify to 9, so root 9, and we know that root 9 is 3. All right, number 6, example number 6. We're going to have the fourth root of 1024 x to the 16th over, let me see if I can draw that nicer, over the fourth root of, we'll say 4x. So here it gets slightly more complicated. We have a variable in our denominator. Well, we have a variable in general. We haven't done that yet. The rules still apply for variables as regular numbers, right? So both of these are the fourth roots. So I can put those together, 1024 x to the 16th over 4x. Our rules apply just like before, where we'd have a variable on the top and bottom of the denominator of a fraction. So we're going to reduce here, and we'd have the fourth root of, what do we have the fourth root of? 256 x to the 15th, right? 1x cancels from top and bottom. From that, there is a fourth root of 256, and it is 4. And then our x's, well, you know what? I'll just leave them under there for just a second. The fourth root of x to the 15th. Now, there's a few different ways to do this. But what I'm going to do is I'm just going to write all my x's out. I'm just going to write a bunch of them. So I have 4, and then the fourth root, and I'm going to write 15 x's here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I know a lot of people can do this in their head, but I just want to be able to show you another way to see this. So we're doing the fourth root, so we're looking for groups of 4. So I'm just going to highlight groups of 4. So we have 1, 2, 3, and then we have 3 left over. Actually, did I do that correctly? I have 4, 8, 12, 13, 14, 15. Yeah. All right. So I can have 3 that come outside, so I'm going to have the 4 times x to the third, because 3 x's came outside, and then I have the 4th root of x cubed. Normally we take the multiplication symbol out, and our final answer is going to be 4x cubed, the 4th root of x cubed. And that's our answer. All right, 2 more problems. For number 7, we're going to say we have the square root of x cubed over the square root of 5xy. This is one of them that we're going to have to rationalize the denominator at the end. So we'll start off, they're both square roots, so we can put them all under one big root with the fraction. So I'm going to have one big root, and then my fraction, so I'll have x cubed over 5xy. My x's can cancel on top and bottom, so I'm going to have the square root of x squared over 5y. And then normally at this point, to be able to think about it a little bit clearer, I like to split the root back up, right? After we've simplified it as much as we can, I like to split it back up over the fraction bar. So I'm going to turn this back into the square root of x squared over 5y. Oh, excuse me, over the square root of 5y. Now, we can't have a root in the denominator, so we want to get rid of it. And what we're going to do is we're going to multiply by 1 in a very fancy way. The bottom is a square root, so I need a pair of 5's and a pair of y's. So I'm going to multiply by another root 5 and another root y. And then on top, I have to do the same thing because we're multiplying by 1, right? Think about that. Those 2 on top and bottom can cancel, and we'd just be multiplying by 1. So on top now we would have 5x squared y, whereas on the bottom we multiplied by root 5y and root 5y, so together it's just 5y. The top of it, we pull the x squared out, and we're going to have x root 5y over 5y. And there we are. All right, last problem, number 8. We're going to do the 4th root of 2 over the 4th root of 3x. So here it's a little bit harder to think about because in the last one we only needed a pair because it was square root, right? This one it's the 4th root, so we need a pair or a group of 4. So there's nothing really that we can simplify with the fraction if we would put them together. But what we're going to have to deal with is how do we get a group of 4 3's and a group of 4 x's on the bottom to come out of that root. That way we can rationalize the denominator. And what we're going to do is we're going to multiply by something under a 4th root again. Right, we're going to multiply by a fancy 1. And we have 1 3. Well, we need 4 3's, so I'm going to multiply by 3 more, so 3 cubed. And then I have 1 x on the bottom. I need 4 of them, so I'm going to multiply by x cubed. Right. Now, whenever I multiply right across the bottom, if I multiplied those together, I'd have a 3 to the 4th and an x to the 4th. And whenever I take the 4th root, I'll just have plain old 3 and plain old x. So let's do that. So I'm going to have on top I'll have 4th root of 2 times 3 cubed times x cubed. And on bottom, I'll just have 3x. And we could multiply those out, but I think I'm just going to leave it like that. So that's a good example of what we have to do if we have a root that is larger than 2, right? The square root, or the cubed root, the 4th root, the 5th root. You'll have to make sure that they add up to have a group of 4, a group of 5, a group of 6. All right, that's all.